Greetings, everybody. So we are continuing our videos on solving systems of differential equations using the Laplace transform. In the previous video, we got some examples on the free response and the forced response and the combined response. And we considered stepping input as an example. So here I'm going to solve the same differential equation. But in this case, let's start. I'm going to give you another input. And for that matter, the input here is going to be, oops, I'm sorry, a much simpler case. You will see why in a moment. Okay, so I'm going to give as an input delta taf, where delta, of course, is the impulse function, okay? So in this situation, we are trying to solve and find what is called the impulse response, okay? Let me remind everybody what is the impulse. Impulse means that at time zero, I'm pretty much, just like kicking or punching the system. So I'm giving it a big energy, but on a very, very short time interval, okay? So this situation is actually much easier because in this case, the solution is much easier to acquire. So let's see why. The reason this is because the Laplace transform of the impulse function is much easier to compute. Of course, here I should also mention that the system is starting from zero initial conditions, right? So when I'm taking the Laplace transform, things are much easier for me. Let's see. So we have for s of y over s, nice, plus 3 times y of s, and this is equal to delta s. Okay. So squared plus 4s, let's factor everything together. This is equal to y multiplied by y of s. This is equal to delta s. And at this point, I can also find the transfer function of the system, right? Which is the relation between the Laplace of the output over the Laplace of the input. Remember, this is for any type of input, so we don't replace the value of delta s here. So this is the transfer function of the system, right? Okay, I think we should get used to that because we are going to use it many, many times in later sessions. So from this, I can obtain that the output is the Laplace of the input multiplied by the transfer function, and then this is s squared plus 4s plus 3. Nice. So this is, remember, what's the Laplace transform of delta s? This is equal to 1. Okay, so that's why I didn't add any more terms right here. And this we have solved from a previous video. This is s plus 1 multiplied by s plus 3. And this is because, let me write it more pretty. This is because we have found the roots in a previous video. So we can break this down into individual fractions. Nice. And now what we need to do is only find a and b. And let's find them. A is the limit. Let us remember what are we going to do here. S plus 1 as s goes to minus 1 of this whole fraction right here. So we have 1 over s plus 1 multiplied by s plus 3. This gets removed. So we have 1 over minus 1 plus 3. We have 1, I'm sorry, this is equal to 1 over 2. Nice. And then we do the exact same thing for beta. This is the limit as s goes to minus 3, s plus 3 multiplied by 1 over s plus 1 multiplied by s plus 3. This gets removed. So we have 1 over minus 3 plus 1, which is minus 1 second. All right. So this is it. We found them. And pretty much this means that we are done with solving this exercise. Because now, let me write everything down. We have that the Laplace of the output is 1 second of multiplied by 1 over s plus 1 minus 1 second of 1 over s plus 3. And now taking the inverse Laplace transform, I obtain that the output is 1 second of epsilon to minus t, u to t, u of t, minus 1 over 2 of exponential minus 3 times t multiplied by u of t. Right. And this is it. We have solved the differential equation for a for an impulse response. And what's the situation here? It is very easy to plot this function because if I make a graph right here, what do I have? All right. I'm starting from 0, obviously, because here I can easily compute that x of 0, y of 0 is 1 over 2 minus 1 over 2, so it's 0. And then what do we have? We have two different terms. One is positive, one is negative. And both of them uh, converge to 0, right? So practically their difference will look something like that. Okay. Oops, sorry. All right. So the system will first move towards the positive position, but then as both of these terms go to 0, eventually this response will die out and go back down to 0. Okay, so this is the impulse response, where we simply kick the system at time 0 and see how it behaves. Okay, simple as that. So as you can understand, compared to the step response, actually the impulse response is much easier to compute because the impulse function has a Laplace transform just equal to 1. Okay, so this is it for the impulse response, and any questions that you have, write them down below. Okay, thank you very much.